jump to label. Two instructions, jump and label. First one is jump to, and the second one is just a label. These are used for if you want to call it skipping logic. So a label is a benign instruction. It really is not even an instruction. It is just a label. Literally, it's where to go to. When you say jump to 3, then you're saying jump to label 3. If you're saying jump to 175, you're saying jump to label 175. So you can look at labels like flags on a golf course. They're really arbitrary, even though they try to put the flag that has a 1 on it in hole number 1 in the cup. Really, they could take those 18 flags for an 18-hole golf course and mix and match and put them anywhere they want. And if you're playing according to the scorecard, you're not even really looking at the flag. So keep in mind that labels are just arbitrary markings in your program. Now you put them in specific locations, but what you call them really doesn't matter. So if you want to jump to a label and you say jump to 1, then the label also has to be 1. That's the only criteria. But you don't have to start at 1 and then 2 and then 3. It really doesn't make any difference what order that you put them in. If you only have one label in your whole program, you can make it any number you want within the range of allowable values as signed integers. Here's a little program that you typed in and then downloaded into your processor that demonstrates the jump to label. This piece of code demonstrates the most appropriate use of jump to label, and that is jumping forward in your program. In another lab, we will show you what happens when you jump backwards in the program. So if we look at these 5 rungs, rung 0 through rung 4, in rung 0, if input 0 is on, that instruction is true. The output instruction, which is a jump instruction, says to jump to label 10. Now the Q2 is put in there automatically. All you had to do was enter the actual label of 10. Q2 means that it's a jump, and the 2 is the ladder file. In this case, you only had one ladder file 2. If you had put in a jump to label and say ladder file 6, then it would say Q6. But all you entered was the 10. Okay, so if rung 0 is true, you're going to jump to label 10. If you scan down through the program, you can see in rung 2 there's a label 10. Which means if rung 0 is true, you're going to skip rung 1. It will be literally as if the rung was not even in the program. And then in rung 2, if that rung is true, if input 2 is on, the output instruction is a jump to label 20. If you scan down, you'll see label 20 is the last rung, rung 4, and rung 4 is an unconditional rung, meaning it has no permissives. A label instruction has no activity. It doesn't activate anything. It's strictly a marker, so when you put in a jump, you have a place to jump to. So rung 4 behaves just the same as if the label wasn't there. It's unconditional. There are no permissives. B300 will always be on. Now, if rung 2 is not true, in other words, input 2 is not on, then we won't execute that rung, and the done bit will turn on output 0 if the timer is done. However, if you jumped over rung 1, then the timer is not accumulating. The done bit will never go true, it'll never go high or 1, and that rung will never be true. Okay, so let's execute the logic. With all inputs off, switch on only input 1. After 5 seconds, the done bit should be on and the output LED, output 0, should be illuminated. Switch input 1 off, and the timer instruction should reset timer data type at memory location T4:0. This is the normal operation of this logic without the jump to labels active. Okay, with all inputs off, switch on only input 0 and then switch on input 1. Does rung 1 appear to be true? Yes, it does. However, the rung is not true in the sense that you're skipping across it. It's not being executed, so the rung can't be true unless the rung is actually being executed and all the permissives are true. But it does look true. Is the TON instruction instructing T40 to accumulate? No, because the rung is not being executed. So the TON instruction is not addressing T40. It's just not being executed. With inputs 0 and 1 on, switch on input 2 also. Then switch off input 0. Did the TON instruction instruct T40 to accumulate successfully? Yes. When the timer data type timed out, did the done bit change to the on state? Yes. Does rung 0 appear to be true? Yes, it does. Did the rung set memory location output 0 to the on state? No. The rung looks true, but it's not true because it's not being executed. Only rungs that are executed can be true or false. The previous rung is true and executed a jump over the rung that controls memory location output 0. Now we're going to jump backwards, jump to label. And there are legitimate reasons that you might want to do this. You might want to perform multiple executions of a short piece of code, and you would want to do it for a set quantity of scans or a set quantity of executions. So if we look at this logic, now when you first look at this logic, it may not be apparent what's going on here. Since you did the lab, then you've already observed this behavior. First of all, we had you delete all of your logic, and then in ladder 2, we had you program a jump to subroutine to jump to file 12 if input 0 was on. And this was just a way for you to turn on and off the logic. Then in ladder 12, we had you enter the rungs that you see here, 5 rungs of logic, save, download, and go online. All inputs off. If we look at the logic in ladder 12, rung 0 won't be true until the control data type R60 has incremented to position 5. So R6:0.POS position would have to be 5 before this instruction is true, and we jump to label 143. Now the reason that I use label 143 is just to show that it's arbitrary. It doesn't have to be label 1. You don't have to start with 1, then 2, then 3. You can put in anything you want. It's just a label. So when you first start executing this logic, rung 0 will be false because you have not incremented R60 yet. We go to rung 1, and B301, that bit will be off, which means the instruction is true. However, if rung 1 is true, it will execute the sequencer load instruction. It will load a value from N70 to N710, linked to 5. So it will execute one execution of the instruction against these data locations. But it will also set B301 to the on state or to 1, which means that this rung will be false the next time through, because if you look at the permissive was that B31 had to be off for this rung to be true. But now we're turning this bit on. If we go to the next rung, rung 2, and we look, it says less than 5. If it's less than 5, if the position, our 60 position, is less than 5, then we jump to 7. Okay, and 7 is jumping backwards. We're jumping from rung 2 back to rung 1. And of course, after we've executed the SQL once, we're going to be equal to 1. So it will be less than 5. We'll jump backwards to 7. But this time, B31 is on because we set it on the last execution of the SQL. But this time, that instruction is false. There is no false execution for an SQL instruction, but there is for the output energized, the OTE. The false execution is to set B31 to 0. We drop down. We look at rung 2. Rung 2 is still true, which causes us to jump backwards one rung to rung 1. Now, since we just turned B31 off, that instruction will be true. We'll execute the SQL and set B31 back to 1, which means that every other time that we execute rung 1, it will be true, and every other time it will be false. So we'll have to loop, and the reason I did this was to increase the number of loopbacks to a number higher than the actual length of the SQL, just to demonstrate behavior and give you something to think about. This will continue until we get to our 60 position being equal to 5. In other words, it went from 0 to 1, 1 to 2, 2 to 3, 3 to 3, 4, and 4 to 5. That's 5 executions. Rung 2 will now be false, so we won't jump to 7. Instead, it'll just go to the next rung, rung 3, which is an unconditional rung that turns on B30. Then it'll go right to rung 4. If input 1 is on, we will fill N70 with zeros, and we will reset our SQL. We'll reset R60 back to scratch. Now, as it explained in the manual, rung 0 in ladder 2 allows you to enable, disable ladder 12. The heart of ladder 12 is the logic in rung 1. If this rung is being scanned, it will be true every other scan. If B31 is off, the rung is true, and the SQL increments one position, loading a value from N711 through N715 and sets B31 on. The next scan, since B31 is on, the rung is false and sets B31 off. The SQL is silent, not having a false execution. The first scan through ladder 12, rung 0 is false, no jump, B31 is off, and rung 1 is true, incrementing our 60 position integer to 1 and loading the value. Sets B31. Rung 2 is true and jumps back to rung 1 and continues to loop back until the position register in the control data type R60 is equal to 5. Rung 0 is now true and jumps to rung 3 every scan. In other words, this will not continue to create loopbacks once it's gone through 5 increments until you execute rung 4. When you turn on inputs 1, that clears R60, and it also clears N70, and you can start over again. So this is just a little demonstration of how you would jump backwards. Why you would jump backwards. If you want to execute, in this case, rung 1 5 times and then go on with the program. In some cases, you can use something called indexed or indirect addressing, where each time you execute rung 1, you also change the address. So the next time through, the code is actually working with a different address. In this case, it's loading a value into a different location. So it actually does something different each of the 5 executions. Another view of this same logic, only this time we're going to add a little animation. Rung 0 in ladder 2 goes true. The JSR executes and sends us to ladder 12. The first rung is false, so we don't jump to label 143. Instead, we drop down to rung 1. Rung 1 is true because B31 is off. So we execute the SQL, which is going to load from N710, length of 5. So N710, length of 5, 10, 11, 12, 13, 14. Now those are the actual names or tag names or pointers for those memory locations. And we do that just so we can keep track, then we know what registers we're working with. We're working with N7 10 through 14. So we're going to use values 10 through 14. So anyway, we're going to load these into N70 for a length of 5. So starting with N710, into N70 length of 5, position 0, we load a 10 from N710 into N70. Then we set B31 to 1, which is now going to make this rung false. Because we are less than 5, then this rung is true. We jump backwards to 7. But this rung is false, so we don't execute this rung. Because it's still less than 5, we jump back to 7, only this time it's true, and we start the process over again. Source N710, now we're in position 1. So we load (11) from position 1 in the source to position 1 in the file. Turn on B31, which makes that rung false. Now we're not incrementing R6 in our slide. Okay, so we didn't, when I did the screen captures, I didn't capture each step exactly the way the logic would look. So you don't see that R6 register position is incrementing from 0, 1, 2, 3, 4, 5. But once it is 5, then rung 0 is true. The position is equal to 5, source B, 5, and we'll jump to 143. So we have a jump forward and a jump backwards. The logic loops through rungs 0 and 2 until rung 2 that R60 position equals 5, and then rung 0 is true and jumps over rungs 1 and 2 until memory location 1 is set to 1. And of course, this may or may not have occurred to you, but in looking at this logic, rung 0 of ladder 2 is true. The JSR is executing. If you look at ladder 12, it appears that rung 4 is resetting N70, that file, back to zeros and resetting the control data type R6:0, and it is. Considering this, you might think that if we are continually resetting R6 back to 0, that rung 0 of ladder 12 would never go true, never jump to 143, and we would never reset. However, if you think about this, basically what's happening is this is executing so fast you just can't see it. But you are actually continually executing this code. So let's do this real slowly here. Rung 0 right now appears to be false, and it actually is false. You might think that this thing is continually looping between rungs 1 and 2. Rung 2 appears to be true continuously. In other words, if you look at just rung 2, 0 is less than 5, so you would be jumping backwards. So if you didn't know any better, you might think that this logic is continually jumping backwards to rung 1 because rung 2 appears never to go true, or I'm sorry, never appears to be false and go on through the rest of the logic. The logic does loop through rungs 1 and 2 until rung 2 is false. Rung 3 never goes false, and rung 4 clears the registers. But more importantly, resets the control data structure to allow another loop cycle after the logic has gone full circle. As long as the scan time does not exceed the watchdog timer preset, the watchdog timer will not time out and fault the processor. The key to understanding what's going on here, rung 2 goes false after 10 loops. The control data type resets for one scan, and then the sequence repeats itself. It's just too fast to follow with screen videos and the human eye. So it is executing perfectly normal, but the minute that rung 0 is true, the instant that rung 0 is true, it jumps to 143, and then because input 1 is on, it clears N70 and resets R60, and then the next time through it runs through 10 loops, 10 back to 1, 10, or I'm sorry, rung 2 back to 1, 2 back to 1, 10 times, and then clears again. It's just too fast for the eye to follow. To further illustrate this, we had you add, no pun intended, a little more logic in here. We wanted to see how many times rung 1 was approached or was in the program. Remember, when you jump over something, it's as if it's not even there. You have two add instructions in rung 1. You have one that actually increments every time we do an SQL and every time we set B3 1 to 1. Because B3 1 is false or off, to make the instruction true to execute the SQL, it's on and off every other scan. So remember, it takes 10 scans through. So we have two add instructions, one to the right of the true if off B3 1 and then one to the left. And then we also enhanced rung 4, so whenever you flipped on input 1, besides clearing N70, resetting R60, it also clears N720 and N721, which are the registers that we're incrementing. Okay, so you cleared all the loaded values and reset by toggling input 1 on then off. Run the logic through again. The add instruction increments on every true scan. True if on B3 or true if off B3 1 separates these two add instructions. How many scans did the jump to label 7 allow? 10. How many scans actually reached the SQL? 5. So all of this logic was done just to trap a little information in an area that's just too fast for the eye to follow, too fast for the screen to follow. Now, this isn't something that you would do in a real application unless you were debugging code that you'd written to actually check to see what it was doing.